Assalamualaikum dan salam sejahtera. So we continue our lecture on boundary layer. So now I would like to explain a little bit in details about what is boundary layer. So inviscid flow is the flow of an inviscid fluid in which the viscosity of fluid is equal to 0. So though there are limited examples of inviscid fluid known as superfluid, inviscid flow has many applications in fluid dynamics. The Reynolds number of inviscid flow approach infinity as the viscosity approach 0. So uh, so inviscid ini sebenarnya ialah lebih kepada I'm sorry. Okay, in this chapter, so I will show you the formation of boundary layer. So as I said, as I explained previously, if you have one liquid here moving from left to right, and if we don't have any obstacle if we don't have any objects, we found that the velocity is remain constant. So mean the velocity is remain undisturbed. So I show you the video so you could imagine actually the white rectangular area in that video is actually represent the velocity profile of this uniform flow. So the word uniform flow here is learned in previous chapter. Okay, so and then when this uniform flow on surface like this, and I already explained, so our focus in this chapter is using the thin flat plate. So we are using thin flat plate. Okay, why? Because we want focus on the shear stress that occur on this surface. So and then when the real fluid flow on a thin flat plate like this one, so the no slip condition occur at this situation. So the no slip condition occur at this one, and then so it will give us a zero velocity. Okay, so here you need very carefully, because in boundary layer chapter we will have two types of U, alphabet U. Small u will show the velocity inside the velocity distribution, and the capital U is the velocity for uniform flow. So uniform flow here, I think in previous chapter we use U, but U that used for uniform flow is actually the capital U. And then to differentiate between capital U and U, in my handwriting, I always write like this. So U with a bar on it. So this is the uniform flow. Okay, and the small u here showing the velocity inside the velocity distribution. So and then, okay, so I will explain about the velocity distribution later on. So and then this is the formation of boundary layer. So again, we have a laminar boundary layer, we have a transition, and also we have the turbulent boundary layer. So first, we will learn about what is boundary layer. Later on, we will learn how to calculate or how to solve problem for laminar boundary layer. And then next, in second half of this lecture, in these 3 weeks before you have your mid-sem break, so we will learn about the calculation for turbulent boundary layer. Okay, so we go back here because I would like to explain the formation of boundary layer. So let me see the, okay. Okay, I will explain with this slide. So, okay, so you know that at this point, the velocity is equal to 0. So, and then the velocity for this molecule can travel a little bit faster. And then here, the molecule here will travel a little faster than the second one. And at certain point, the molecule will travel as fast as the uniform flow velocity. So means that at this point, the velocity is actually similar of its back to its normal velocity. So this is for x equal to 1, for example, mean at location x equal to 1. However, in x equal to 2, mean at another location in x-axis, we found that here the velocity is equal to 0, but the thickness of this one, okay, the molecule, the area, the location where the area is back to its normal velocity is a little bit thicker or a little bit longer compared to the thickness at x equal to 1. Okay, so and then what scientists do is compared to the experimental. I already show you a video showing you that if we move this plate, if we move this plate on the fluid, so you will see a layer. So that layer is actually equivalent to, if we point here, for example, we mark, okay, for example, we mark one point here where the molecule is moving at the same speed of the uniform flow. So we mark another point here where the velocity is moving with the same velocity of the uniform flow. And then if we connect all the point there, we could draw a line like this one. So we could say that the area inside this one is called a boundary layer. So this is not a boundary layer because at this area, the velocity is constant. Mean the velocity is always almost the same. So it will have same velocity at any location in this area. However, in boundary layer, the velocity is changed, is varied, because the velocity this called, so the difference of velocity here is called the velocity distribution. Okay, so and then I would like to explain what is, there are three terms that you should know to evaluate boundary layer. One is delta, which called the boundary layer thickness. So we go back to this one, okay. Okay, as I said, so if we draw the velocity distribution like this, okay, and then we create a locus, and we found that we could draw a layer like this one. And this layer is actually visible in experimental works. So as I show you in previous video, you could see clearly a layer on the thin flat plate. So means that the boundary layer is actually a physical phenomenon. You could prove it in experimental. So means that if you could prove it in experimental, means we could calculate the thickness of the boundary layer. Okay, the first term that you should know is the value of delta. So delta means the boundary layer thickness. So what is boundary layer thickness? You should know that it is the thickness, means the length, the distance from this surface until this point. Okay, but you must know at what point you must to stop. Okay, whether you want to take the 100% or 99%, so it's depend on the definition. Okay, let's say we see the definition of boundary layer thickness. So the definition of boundary layer thickness is a distance from the surface where the local velocity, so the word local velocity here can be written as small u, equals 99%. So you must remember 99%. So this is fixed, okay, of the free stream velocity, which is the uniform flow, which is can be written as capital U. So in your handwriting, because you will answer this in test 1 and also in final exam by using your handwriting, please write carefully. So you could write U, small u like this, and I propose to you to write your capital U like this with U and bar on it. Okay. Okay. Please do not write U and bar like this. Okay, so please write like this, and please do not write like this because it will confuse the reader. Okay, this is just to differentiate between the capital U and small u. So this is the definition of boundary layer thickness. Okay, the idea is a distance from the surface where the local velocity equal 99% of the free stream velocity. So means that if we have a plate like this one, so we know the molecule here is U is equal to 0. So and then the value of velocity is keep increasing. Okay, let's say we have a molecule here is 100%. Okay, so we cannot take the 100%, so we take the molecule which only have 99%. 99% of free stream velocity. So means that the locus here is actually 99% of the velocity, and the velocity here, okay, this is the 99% velocity, and this is the 100% velocity. So this is maybe the simple idea to show where is the boundary layer. So the word boundary itself showing that you should know what is the boundary between the uniform flow and the velocity distribution. Okay, so please remember this definition. So and then we need to write this definition into the mathematical equation. So the mathematical equation can be written is like this. So we could write that the boundary layer thickness can be expressed as delta is equal to y, which is u is equal 0.99 capital U. So from this equation, you should know that the delta here mean the thickness here is the value of y-axis. So means that this is the y-axis. So the boundary layer thickness mean the distance at y-axis. And you know y-axis is 90 degree from the x-axis. Please do not measure from here to here or from here to here. So you should measure according to y-axis, mean from here to here. Okay. And then where you want to stop. So you start with u equal to 0 and you stop at u equal to 99% of capital U. So the word capital U here will reflect the velocity for the uniform flow. So 0.99 mean 99%. Okay, so this is the mathematical equation for boundary layer thickness. You need to remember this. So and then because this equation is very simple, so means that the delta here is the distance on y-axis from u equals 0 to u equal 99% capital U. So means that the unit for this delta is actually in millimeter. Mean you could use millimeter, you could use meter, inch, and so on. So means that it is real because you could measure it from experimental work. So you could see the video later on. Okay, because this equation is very simple, you cannot get more information from this. So means that you need to create another equation from boundary layer to help you to calculate the value of delta. Okay, because if you just use this equation, you need to measure the value of y from the experimental work. So if you are not capable to do the experimental, so means we try to do by using the calculation. So because we are try to using calculation, so means that before we create our equation, we must make sure that our situation, our idea is fulfilled two basic physics idea. One is called the conservation of mass. Okay, so to make sure that the conservation of mass is fulfilled, so we need to understand, or we create another parameter called displacement thickness delta star. Thickness is not a physical phenomenon, so means we can show displacement in experimental work. So displacement thickness is actually an imaginary terms that you must use in your calculation. Boundary layer thickness previously, here boundary layer thickness is the real one, the real phenomenon. You could measure it in experimental work. But for displacement thickness, it is not. It is just to correct your equation. We need to do some correction in our equation to make sure that the equation that we use will fulfill the idea of mechanical engineering, the idea of physics. Okay, one of them is the idea of conservation of mass. Okay, so what is displacement thickness? Okay, displacement thickness is the distance the surface would have to move in y direction to reduce the flow passing by a volume equivalent to the real effect of the boundary layer. So this is the common official terms of displacement thickness. So in simple way, we could say that displacement thickness is an additional thickness that we need to add in our equation to make sure that it is fulfill the idea of conservation of mass. Okay. Then, so we comes with this diagram. So I hope you could draw this diagram very, very good. Okay. For example, we have a thin plate like this one. So, and then we have a uniform flow like this. So the velocity distribution is in rectangular area. So, and then when the flow flows over the flat plate, the velocity distribution occur. So the velocity distribution will occur like this one. So we have no slip condition here. So the molecules stick very hard. So, and then it create a distribution like this one. Okay, so from this situation, you could see that the area here is not the same with the area inlet here. So means that the conservation of mass mean the total mass at inlet is not the same with the total mass at the outlet here. So, and it is weird. In physics, we know that the conservation of mass must be fulfilled. The mass for inlet must be equal to the mass at the outlet. So what we do here is actually we add another layer here to make sure that the mass is conserved, means the total mass at inlet is now equal to the total mass at the outlet because we add a new layer here. So the thickness of this layer is mentioned as delta star. So that's why we call this one as a displacement thickness. So displacement means we displace the thickness. Okay. So now we try to calculate the idea of mass. Okay, so previously in fluid mechanics 1, you already learned about the density. So the equation for density is mass over volume. It can be mentioned as mass over volume, M over V. Okay, please make sure that you understand this V is volume. And then to calculate the volume, to calculate the mass, okay, to calculate the mass, you could calculate as M equal to rho V. So you just bring the V here from right to the left, so you could calculate the mass. So the rho is the density, so means it is the density of the fluid. So and then to calculate the volume here, so it is okay for us to calculate the volume of this velocity distribution, means the volume for this area. So the volume is, we could get the length of this one, we multiply with its height here, and then we multiply with its width. So if you have a 3D, so you need to multiply with the width. And then to simplify our calculation, okay, we just assume that the width here is equal to 1 unit. So we just assume that the width here is 1 and the width at here is also 1 unit. So, and then we just put 1 here. So we could simplify our calculation. So to have the value of mass here by multiplying density, velocity, and also the thickness. So here, this is the thickness. And we know that the definition of boundary layer thickness is the distance on y-axis from u equal to 0 here, u equal to 0 until u equal to 99%. So means that we could assume that the height of this one is actually the delta. So okay, so means that the important things that you need to remember is how to calculate the value of mass. Okay, so we just assume that the width is equal to 1, so we could simplify our equation become rho, velocity, and thickness. Okay, so how to calculate the conservation of mass? So the idea is we must make sure that the input is equal to output. So according to this diagram, you could say that this is the input and we have two output. Mean we have the output from here, B, and the output from C. Okay, so and then we could calculate. Okay, the simple one is the mass for A. So the mass for A can be written as rho, U, and delta. So you know that I already show you here. We calculate rho, U, the distance of this one, and the delta, the height of this one. So and then you will get rho, U, delta. So and then we could calculate the mass of MC. So MC here is the area of this one. Okay, so this is very easy to calculate because the shape is rectangular. So we just multiply with the capital U here and the thickness of this area, which is delta star. So that's why we have rho, U, and delta star. So then we need to calculate the value, the mass from the B area. So for B area, we have a little bit problem because the velocity here is not the same. So we cannot just take one velocity to fulfill the equation. We cannot do that because the velocity is vary from point to point. So what we need to do is we need to use the idea of integration. So I think you already know how to do this. Okay, because in chapter 1 you learn about the previously in fleet 1 you learn about the integral method. So it is the same idea actually. So we start with a small area in area B. So let's say we have a small area of this one. Okay, so the small area, we assume it is in rectangular shape. So we could assume that the thickness of that rectangular shape is dy. So and then the velocity here is small u. So and then we could calculate the area, the mass for that small area is rho small u and dy. So and then to get the total mass for that area, means the total mass for this one, what we need to do is we need to integrate all the equation. So we integrate with limit from y equal to 0 until y equal to delta. So that's why here we write integration of rho u dy with from 0 to delta. So and then because we want to calculate the value of delta star, so we rearrange this equation, we could write like this one. So and then because we have one terms without integration and one terms with integration, what we need to do is we just reverse calculation for this one into the integral format. So we could say that it can be written as integral of 0 to delta rho u dy. So means that if you change this into the integral of 0 delta rho u dy, you solve the that integration, so you will get rho u delta. So means that we replace this term into integral 0 delta rho u dy minus rho integral rho u dy. We could simplify it as this one. So and then we bring the rho u here to the right hand side. So we have the over rho u like this one. So and then we could simplify the value until you get the final terms like this. So and then we could say that the equation for displacement thickness can be written as this one. So please remember this equation. So please make sure that you could draw the diagram. You could draw the, calculate the conservation of mass, the idea, and then you could prove the value of delta star can be written as integration of integral 0 to delta 1 minus u over u dy. Please make sure that you write small u and capital U in the right place. So normally I will write 1 minus u over capital U. So I will write like this one. So you could differentiate it very well. Okay. So this is the equation for the displacement thickness. Okay, so and then another term that you should know is the momentum thickness. Okay, the momentum thickness is theta. The official terms, the official definition is this one. The distance by which a surface would have to be moved parallel to itself toward the reference plane is an inviscid fluid stream of velocity u to give the same total momentum as exists between the surface at the reference plane and the reference plane in a real fluid. So the simple words is, again, we need to calibrate, we need to modify, to do a correction with our equation to make sure that the conservation of momentum will be fulfilled. Okay, first, conservation of mass, then we get the displacement thickness, then we do another correction to make sure that the momentum, conservation of momentum will be conserved, will be fulfilled, then we get the momentum thickness. Okay, so the idea is very simple. I could do this a little bit faster. So we still use the same diagram. So this is the uniform flow. So and then when it flow past the flat plate, so the velocity distribution occur. So and then we already have the momentum, the displacement thickness here, and then we need to add another layer, another thickness here to make sure that the momentum thickness will be fulfilled. So the thickness here is theta. So and then what we need to calculate is we must make sure that the total momentum, means momentum at inlet, must be equal to the momentum at outlet. So and then the momentum, the equation for momentum can be write as mass time velocity. So the value of mass, okay, you could refer from the previous calculation. Okay, and then we could simplify this calculation by using this table. Okay, so for example, for inlet, the mass is rho u delta and the velocity is u. So and then the simple one is the rho u theta, the top one here. So this is theta because it is rectangular shape, so we could calculate it very easy. So we have rho u theta and the velocity is u. So and then the second one is this area. So the shape is rectangular, so we could calculate as rho u delta star and u. So and then we need to calculate this area because this area, it is not even area. It is the velocity is keep changing. So we start with a small area of this one. So if you write the momentum for the small area here, okay, you could calculate as this one. So you could calculate as rho u dy. It is the mass, and then you need to integrate it because the velocity is keep changing, and the velocity can be written as small u. So what you could do is, by using this equation, you just substitute the total momentum at inlet like this one. So this is the mass and this is the velocity. So this is the momentum for the velocity distribution. This is the momentum for the displacement thickness, and this is the momentum for another thickness. So and then because we are so now here, okay, the step is, now we have two unknown parameter. One is delta star and one is theta. So to simplify this equation, we replace the value of delta star with this equation, because this equation is already proved in previous calculation. So we substitute the value of delta star with this equation, then you will get this term. So and then because we are calculating, we try to define what is the value of theta. So we bring theta to the left hand side, so we could write like this. So and then if you do this at home, you will find that rho u square theta can be written of this one. So and then we bring the rho u square to right hand side, and then we could simplify this into this term. So finally we could say that the momentum thickness, the equation for momentum thickness can be written as theta equal integral 0 to delta u over u 1 minus u over u dy. So please remember this equation. So you have three equations for today. You have a delta, delta star, and theta. Please make sure that you know how to write, how to explain the formation of boundary layer. You know how to write the equation for boundary layer thickness, displacement thickness, and momentum thickness.